Okay, I'm going to give a brief overview of surface integrals as physical laws of nature. And there's actually there's many more, but I'll just cover three. So the first one is Gauss's law, and the second one is just you might think of it. I don't think it has a name, but it's called the conservation law. And the second one is called Fourier's law, and it's governed by heat, and it governs heat flow. And the second one, it governs fluid flow. And of course, Gauss's law, it is about it's not a flow, but it's about electric charge. There's actually a Gauss's law for gravity as well, but I won't cover that. So these all involve surface integrals, actually, and that's kind of the surprising thing. If I state these things really quickly, this Gauss's law says that up to this constant, this epsilon naught is just some constant, that the charge enclosed by some surface, the total charge, I mean, this is actually equal to an integral over that surface of the electric field. And it's actually, I hate to say it, but all these things are kind of the same. So I'm just going to draw something, a kind of similar looking diagram here. So in the fluid case, the setting is actually something called the velocity field. And again, we'll have our normal vector. And the velocity of the fluid, that's the thing that's going to be the dot product. So I'm just going to put a v dot ds here, and there'll be a rho, because we'll need that mass. So this will be the change of total mass in time. Oh, and I also need a minus sign here. The minus sign is because the velocity of it, if fluid's flowing out, that actually corresponds to the velocity vector aligning with the normal vector. So that's why we need a minus sign, because the mass will be going down in that case. So finally, I'm instead just gonna, it's gonna be a little easier for me to use a 1D. So if U of x is the temperature, then roughly speaking, I'll go over these in more detail, but roughly speaking, because temperature flows from high to low, the temperature gradient, it actually corresponds to the direction of heat flow. So what we'll instead put for that dot product is how much of a temperature gradient there is. And then this will be the change in time of the heat flow, or of the heat within this region. And so the common theme here is that all the interesting, all these interesting quantities are determined by boundary behavior. And by boundary, I mean the boundary of the boundary of the solid. And that's our surface. Our surface is playing the role of the boundary of this closed solid region. And it says now that all the interesting quantities, they're actually related to these integrals of these dot products. And the dot product of E, for example, dot n, this is called a flux. And so, for example, this is the electric flux. This will correspond to the mass flux. And this will correspond to the heat flux. And flux means, well, flux is similar to flow. So it tells you how much it's flowing outside of the domain. And all of these laws play essentially pivotal roles in their respective fields, even though these are from completely different fields, right? And as it turns out, these laws have very powerful predictive power, and predictive power is where engineers come in, for example. So I don't need to state the importance of things like this. So in the next videos, I'll be going over these things in more detail.